For this video, we'll be focusing in on electronic transitions of electrons in the hydrogen atom, and the way the electron will become more or less excited depending on whether or not a photon is absorbed or emitted. So the question here states that I'm already in the ground state of hydrogen, and I'm promoting it to some excited state when I absorb a particular wavelength. But then I'm going to lower that wavelength lower that electron's energy state by emitting a photon. So what I'm looking at is a two-step process. So what I have here is a depiction of the first step. I have a ground state energy with a wavelength coming in, but I don't know where I'm going to end up. And since this is a two-step problem, I'm not going to use N final. I'm going to call it N intermediate. Now, according to my formula sheet, I know that the energy of some energy level, some quantized level, is a negative B constant times 1 over that energy level squared. So if I wanted to look at the change in the difference of those energies, it'll be negative B final minus initial, or 1 over N final squared minus 1 over N initial squared. So like I mentioned, I'm not going to use final for this first step. That N final now becomes N intermediate. And I will be looking at looking for that difference in the energy levels here. But I know about energy. I know where that change in energy is coming from. That change in energy is actually coming straight from the light of the energy of the light. So if I know the energy of light, I know how to deal with the difference in those two quantized levels. So the first thing I want to do is I want to find the energy of the light, which is just Planck's constant times frequency. But the speed of light is equal to, not Planck's constant, the frequency times the wavelength. So I can combine these two formulas in terms of wavelength. The energy of light, hc over lambda. Now, one thing that I'd like to point out to everybody is that when you're dealing with quantum chemistry, it would be a very good idea on a constants page to go ahead and multiply h times c and writing it down. Because you don't have to keep writing h and c all the way through. If you've used h times c once, you're going to repetitively use it. So one thing that I will be doing is I'll write everything out in long form, and then I'll just use that simplified version as I continue. But it's always a good idea to find h times c and have that sitting off to the side. Now, doing the algebra, I'm going to solve for the energy using the wavelength. So let's plug everything in now. So 6.626 times 10 to the negative 34 joule seconds. Multiply that by the speed of light of 2.998 times 10 to the 8th meters per second. And I'll divide that by my wavelength. So I'm going to go ahead and write it out in terms of nanometers. And within the denominator, I'll go ahead and include the unit conversion. So that for every 1 meter, I'll have 1 billion nanometers. So double checking my units to make sure everything cancels. My nanometers will cancel out. My meters in the denominator will cancel out with the meters in the numerator. And the seconds will also cancel out both in the numerator, leaving me with a value of joules. So the energy associated with the first light, the first part anyway, is going to be a value, I have it written down here, of a value of 2.04286 times 10 to the negative 18 joules. And since my wavelength is in 4 sig figs, I'm going to underline 4 sig figs. And as an aside, h times c is going to be 1.986475 times 10 to the negative 25th joule meters, just so I'm consistent with what I told you I was going to do. Now, this energy value is going to be the change in energy that we use for our differences in our quantized energy levels. So the change in energy value is going to be this value. So going back to our original formula, the change in energy is equal to negative B times 1 over our intermediate energy level squared minus our initial energy level, but our 1 over our initial energy level squared. But that's just 1. So it's going to be 1 over 1 squared, which is simply just 1. So negative b, 1 over n intermediate squared, minus 1. And I can do some algebra to get everything on the right side. Now, the one thing that I want to point out is that negative in front of b. A lot of times when you have two energy levels, you'll get a delta E value, and you could always use the absolute value of this value to work with the energy of light. But how do we factor in using this negative when we're trying to solve for the energy levels? One thing I want to point out is that if the value of your final level is greater than the initial level, then we want to keep this negative in place. But if the n final is less than n initial, we want to turn this into a positive b. That's going to be the only way that I can keep the energy levels to being a positive value. So that negative only happens if the final energy level is greater than the initial. Okay? So for this problem, we're going to keep the negative in play. So I'm going to first rewrite my formula. And I'm going to divide both sides by negative b. So delta E divided by negative b is equal to 1 over n intermediate squared minus 1. And then I'll move over the negative 1. So 1 minus the change in energy over b is equal to 1 over n intermediate squared. Now, there's a couple more steps in the algebra, but let's go ahead and find the left-hand side first now, shall we? Left-hand side is 1 minus the change in energy, which is 2.04286 times 10 to the negative 18 joules to 4 sig figs. And then I'll divide that by the constant b, which is 2.179 times 10 to the negative 18 joules. And I'm going to get a value of 1 minus 0.937521. And that should be to 4 sig figs. So this value here will be a 0.062479. And this is equal to 1 over the intermediate quantized level squared. The best thing that I can do now is take the inverse of both sides. So I'm going to raise to the negative 1. So 1 over 0.062479 will equal the intermediate energy level squared, because 1 over the intermediate squared is just an intermediate squared. So this value, if I plug it into my calculator, is approximately equal to 16. So my intermediate level is 4. So the electron absorbs 97.24 nanometer wavelength of light, goes to the 4th energy level. But now I've got to descend because I'm going to emit a photon. Now I already know one thing. The second step, my answer will not be n equals 1. If it was n equals 1, then the wavelength of what was absorbed and the wavelength of what is emitted should be the same value. But notice the wavelength is different. So I know my final answer cannot be n equals 1. And since I'm emitting the photon, it's either going to be an energy level of n equals 2 or n equals 3. Because if I'm emitting a photon, I'm dropping the energy of that electron. And the only place I can go is n equals 2 or n equals 3. So my change in my energy for this second step is going to equal negative b times 1 over n final squared, which we don't know yet, minus 1 over n initial, which is our 4 quantity squared, or negative b 1 over n final squared minus 1 over 16. But I know that n final is going to be less than n initial. So I'm going to rewrite my formula as positive b 1 over n final squared minus 1 over 16. And we'll be finding that new change in energy because that new change in energy is just the energy of that second wavelength of light. So the energy of this second light value is just hc over our new lambda value. I already know what my hc value is. It's 1.98. Where to put it? There it is. 6475 times 10 to the negative 25th joule meters. And I'll divide that by my new wavelength of 1,875 nanometers, which I'll go ahead and also do the unit conversion. So I'll divide that by 1 billion. My nanometers will cancel. My meters will cancel, leaving me with the units of joules. And I will write this to 4 significant figures, 1.05945 times 10 to the negative 19 joules to 4 sig figs. And we go back to that algebra. Change in energy is equal to B 1 over n final squared minus 1 over 16. So the change in energy divided by B is equal to 1 over n final squared minus 16, 1 over 16. And now 1 over n final squared will equal 1 over 16 plus the change in energy over B. Because remember, I'm subtracting that negative 1 over 16 by both sides. Remember, I'm subtracting the negative 1 over 16. Okay, so I'm adding to both sides. So I can start plugging in values I know. So 1 over n final squared will equal 1 over 16 plus my 1.05945 times 10 to the negative 19 joules over 2.179 times 10 to the negative 18 joules. And I'll get a value of 1 over 16 plus, where to put it, 0.04861, which is going to be added together 0.111121. And this is equal to 1 over n final squared. Like I did before, take the inverse of both sides, and n final squared is equal to 1 over 0.111121, which is approximately equal to 9. If I do the square root to both sides, n final is equal to 3. So I started at the ground state, one wavelength came in, promoted it up to the n equals 4 energy level, and then emitted a photon to bring it down to the final wavelength, a final energy level of 3.